Inverse kinematics and the way and magic of animation. This is our topic today. I did a video on my script I just published in the asset store where you can download for free a set up and ready to go script to use inverse kinematics. And you have some kind of a chain here, and you can set targets where the chain is just bending towards. So here we go. And you can set a pole, and this pole allows you to set the angle the whole thing should bend to. And this is what we will program today in our little tutorial. We will do this from scratch. The result will be one-to-one the code that is published on GitHub, and you can download it in the asset store. But you will learn a lot about inverse kinematics, and you can even change the code to let it fit to your need. So let's first create a simple asset. We will use the asset in this tutorial. So I will just use this simple cube, scale it, and then add some loop cuts, for example, like so. And this is a very solid object. Go back to object mode and add a single bone, and the single bone will be used to create my armature. So this is an armature, very simple armature. That's it. Export it to Unity. Make sure you add the leaf bones, and you select armature and mesh, and then export the FBX. And in Unity it should look like this. You should have your cube, your armature, and my version doesn't work because I forgot to parent the cube to the armature with automatic weights. You know you've done everything right when you can rotate the model, and it behaves like this. So you could also use just boxes paired to another. It would have the same effect. So that's it. And now we want to have some target. We create a sphere. This is our target. We will position it here at the end. And now we want to do the following. As soon as we move here, the end should be set to this target and everything should bend. This is inverse kinematics. Okay, how to calculate it? Let's go. So I want to briefly explain the algorithm. So basically what you always need is a complete chain length. So we will attach the script here and just go to the parent as long as we want. This will be just a parameter, 1, 2, 3, for example. And then we have something like the length. So, and the first check always is the distance to our target object greater than the length L? So, and if this is the case, it's very easy because we just draw a line here and say, okay, we take this distance and lay it on this vector. For example, if the A target is here, we calculate this vector very easy by subtracting those 2 points and then lay down the points here, and we are done. So this is the easy case. Okay, let's do so by attaching a script here. Maybe I really start with the spheres and then go for the rest. So we attach the script here. We could also attach the script here, but let's start with this one. So we call the script FABRIK IK Fabric because that's the way I called it in my asset store asset. You can download it. The link is in the description, so the script is ready to use. But we will just create it again from scratch. It's attached here. Let's edit it. Okay, let's start by adding some parameters. So we will have the chain length. The default is 2. We will reset it in the editor in the minute. We will have the target and the pole. We do not need the pole right now. This is more advanced stuff. Let's just go with the target. And we need solver parameters, iterations, a delta, a snapback strength. Just ignore them right now. We just need the chain length and the target for now. Okay, back in the editor, we have the final UI for our IK Fabric script. The chain length is 3 and the target is this white sphere here. So we have no idea how this will all look, therefore we draw some gizmos. You can skip this step, but it will help you in general. So just add a method on draw gizmos. This is where we can draw our gizmos. Okay, we start with our current transform and then we iterate through our transform. So we start at 0 and we do this loop until we reach the chain length, and we will just go up. So our new current is always a parent of our current. And we will repeat that as long as we're smaller than the chain length, the current is not equal to null and our parent is not equal to null. If the user is typing some ridiculous high number but his chain is not long enough. So, and here is the code to draw the handles. Handles are just bars in the Unity editor, and you have to import Unity editor here to use them. And they have a color. I draw a wire cube, and this matrix is something where we rotate the world. So you can basically look this up. It's not that hard to understand, but what you want to know is you start at the current position and you stop at your current parent position. And the other things are just calculations to have the matrix right, to have the complete drawing right. And here we go, these are the gizmos. I don't want to really focus on the gizmos, but they really help to understand everything. So here is our current node, and if I maybe reduce the chain length, the chain is shorter and shorter. This chain wouldn't work, so the minimum number is 2. So when I go nearer here, this ball will go up, and this is a complete chain. Okay, let's start with the real code. So at first we create an init function. We will not only call it on awake, but during runtime as well. And the init function some kind of looks like this. So we will create bones. Bones are transforms. Now I have to explain a little bit. So this is a bone, this is a bone, this is a bone, and this in our example. If we have a chain length of 1, 2, 3, we need 4 bones. This means first bone, second bone, or if we count in a correct way, 0 bone, 1, 2, 3, 4 bones. 4 bones, 4 positions. And the bone length is this one. So 0, 1, 2. If you combine all the bone length, you have the complete length. And this is important for our first aspect where we say, okay, if the target is far away from our root, then the complete length, then we do something different. Special handling, we will start with that. Okay, and then same trick as we did before. We set the current pointer to our current transform, and we go through this loop and for every bone and say, okay, we go 1 bone up. So this is the way how we set our bones. We say current bone is a bone on position I. Then we just do some if statement here to differentiate between a leaf bone and a mid bone. The leaf bone is really the last bone, and the last bone has no length. So, and because it has no length, we do not set it, and it doesn't go into the complete length. The bone length of our bone I is just the position and from the bone before and the current position. So back to our example. How does the first iteration looks like? Current is transform. So this is current. And then I start with bones length minus 1. This means this is the index 3 because our chain length is 3 plus 1 is 4. We have 4 bones, and 4 bones minus 1 is 3. So index 3. And it's the last bone, so we do not do anything. So this is the first iteration. We go 1 up, current is here, and this is of course index 2. And here is the bone length 2 is just the bone I plus 1 position, this position, minus the current position. The magnitude is just the distance between those 2 points, and we store it here, and so on. length here, length, point. So 0 is our root bone, and 3 is our leaf bone that should be attached to the target. Okay, let's do something. This is just initialization. On late update, we will really resolve IK. Just a method that we maybe can move it later. And let's do some really simple checks at the beginning. For example, if the target is not set, we will just return. We do not have to do anything, otherwise we will get ugly null pointer exceptions. And if the chain length does not fit to our bone length anymore, we have to init again. So this means we can really change the bone length during runtime with my script. Okay, now let's start with these positions. We will use the FABRIK IK algorithm. So, and therefore we have to get the current positions, do some math on it, and then set it back. So we start every iteration by getting the current position. We do not do any computations on the bones directly. We will have some iterations, and then the result should be set to the bones position. So, and here we go. We do the same thing vice versa. So we set the position to the bone position. Of course, it seems stupid because calculation is missing here. Okay, I switch to paint now, because now we have to check if this position 0 is reachable. So is far away from the target than the complete length. So just check this distance against this distance. So, and these distances are pre-computed partly because we already have the complete length of the chain, and this is this one, and we only need to compute this one and compare it against it. Okay, how do we do it? Just take the target position and subtract the root position and get the squared magnitude and compare it to the complete length. To make things easier, I would say this is how it should be. Just the magnitude is greater than the complete length, but we can square both, and it's still equal. And we have the benefit that this computation is way faster because we do not have to calculate the square root of anything. Okay, now we have to just stretch it. This means we will get this direction, I call it D direction, just the target position minus the position 0. So the bone 0 position is the same as the position 0. And we will just distribute this based on their lengths. So these lengths are equal, this one and this one. And here we go. Just go through every position and say, okay, my new position is the position of my predecessor plus the direction times the bone length of my predecessor to myself. Easy example, we have the position I minus 1. Then this here is the length I minus 1. And then we have the position I. Okay, and as you can see, it's working. It's not working here in this area, but it's already working here in the extreme cases. And this is where we already can apply it here. And there we go, it's moving. You see a flaw, and the flaw is the rotation is not correct. So the position is okay, but the rotation is not yet right. We will fix this, but we will first fix the other one. So I deactivated the script as well. So now let's take this for example. How do we solve this problem? The FABRIK algorithm is made of 2 different steps, a backward step and a forward step. So let's start with the backward step. So what we will do is we will set this one directly here. Just set it there, everything is fine. But if the ball is here, you have a problem because maybe this distance isn't okay. Therefore, you just calculate here a normal vector or a vector with normal length, and then you take this distance 0 for example, and just apply it here so that your second ball maybe moves here. So because then they are 0 apart from another. Then you do the same thing all over again. You draw a line here. See, you have distance 1 here and you have to have it here. Therefore, this ball will move here. And then you draw a line here. You have distance 0. It doesn't fit anymore, so you have to move this ball here. Now, this looks like a banded arm or something. It's way better than before, but you have one problem. You don't want to move this wood. This is unmovable because this is maybe attached to a whole body. So we have to do the same thing back to the target. Apply it, then we have a fresh canvas. So this ball has to move here. We just set it there, and then we draw a line here. And this was distance 1, and we have to keep the distance, and we set the new ball maybe here. And then draw a line again. Distance 2 should be the same as here, distance 2. And then the ball is here, and the same again here. And the ball goes back a little bit. So let me apply this. Maybe it will look like this. So this is one iteration, and as you see, the wood is still in place. This one is close to our target. It's not directly on our target, but it's very close. And it was here before. And this was one iteration. And therefore, we have this parameter called iterations because we do not do it one time. We do it 10 times and 10 times per frame. So this is really a good estimation. You can also try it with one iteration, but if you use 10, it's okay. And we can really stop before we really reach this 10 iterations by saying, okay, if this is nearly at the same position and there's a delta of 0.001, we stop the iterations. We do just maybe one iteration or no iterations at all if the target does not change, and this will save us one time. Okay, it's very simple. We just start with the iteration. So the iteration starts at 0 and stops at the number of iterations. This is our field we have here. So 10 times. It was a 10 in our editor. And then if we are close enough, we just stop. So we stop after 10 iterations, or we break even if our last position is so close to the target that it's closer than the specified delta. And here again, the trick with distances. Okay, let's continue. The back algorithm. Remember, we start at the last ball, and this is position length -1, and then we go back, so we decrease the positions. Okay, I said we set the last one to the target position, and this is what we do. If we are at the very beginning of our iteration, we just set the position to the target position. Otherwise, it's getting a little bit more complicated. So, the position is now the position +1. Now the position is position. This is position +1. This is I +1. So, and we start here. This is the one on the right. And now we need the vector. The vector is just the vector between those two positions. And we normalize the vector so it has a length of 1. And then multiply it by bone length so that we say, okay, these two balls should be always apart with a distance specified in the bone length. And therefore, we set it maybe to here. And that's it. That's the backward part. Okay, the forward part. It's easier because we do not set it to the target. But I already explained we set the root bone back. But in my example, I skipped the index 0, so I didn't touch the root bone at all, so that we can already start by just setting the positions. And the code is exactly the same, it's just reversed. For example, set the position of I will take I minus 1, so the ball to the left, and here it's I plus 1. Here the same, normalized distance, the same as here, just plus and minus, and the bone length, of course, this time to the other side, so bone length minus 1. Okay, let's try it. This case works as expected, and this one looks weird because, yeah, I'm not in a 3-dimensional space. So let's get rid of this. Now we can see it better. Yes, there we go. You see, this is inverse kinematics. You can already start a snake or something. Works pretty good. Let's activate this one. There we go. It doesn't work. It does not look that good. And the reason is just the rotation. So let me demonstrate it. Yeah, I'm rotating now. I'm rotating everything with everything, but normally it's just a way of rotation, and then it works. So the position is now correct. The rotation is not correct, and we do not have a pole. And we do want to have a pole. A pole is something where the complete thing should bend to. I will just show you what it looks like. I created the sphere. Maybe I rename them. And I attach the target and the pole to the corresponding fields. So I can move the pole here and the target here. And you see the whole chain is bending against the pole. You see here up or down or left or right. It doesn't matter. It will help you. For example, if you have an elbow, you would set it like this, and you see, okay, the arm is always bending in that way. What did I do? So I created a normal vector from here to here. Now I have a position and I have a normal vector or a distance vector. And if you have those two things, you can really create a plane. It's an infinite plane. Now I just made it a box, but it's infinitely long. And now what I do is I draw shadows on it. Imagine that the normal is not going out, but going in as sun rays. And then I do the following. I just cast a shadow. So, of course, because this is a normal, the shadow of this thing will be directly here. So they will share the same shadow. And then there's a shadow going down here. And this is the bone. And then there's a shadow of the pole, and this is here. And now you see the plane is really too small. So if I have a bigger plane, this would be here. And now what I do is, what I really can do is just rotate this ball here, or this bone, around this axis. So I can freely move it around this axis. It's really, it doesn't matter. You see here, if this is the axis, I could easily move it here. All the distances are the same. And therefore, I'm searching on the circle the spot where the distance to this pole is minimal. If we have a pole, we do this. Otherwise, we just skip it. And we do it for every position starting from 1 and going to position length -1. So we start not with the root, but with the first one and the position length -1, and we do not do it for the last one. This means in our tiny little example with 3 dots, it's really that simple. This is 0, this is 1, this is 2, and we only do it for this position. And it's completely clear because this is the only position we could move. This is determined by, it's just there, the root bone. We won't change the position, and this is just always set to the target. So the middle bones are the only ones that do really interest us. Okay, let's see the plane. The plane has 2 arguments, a normal and a point. The point is easier, so let's start with the point. The point is just the position. This is I equals 1, so this position here. is the base of our plane, and the plane is pointing towards the position I plus 1. This is the position I plus 1. And here we have the position I minus 1. There we go. Here a long line, and yeah, it creates this plane here. Here we get our plane. Now we do this projections, and it's like the shadows. And the shadows are the closest point on the plane, because we are casting rays in this way here. And if the pole is here, for example, the sun goes down and just creates a shadow here. And a second shadow, for example, if this would be a little bit more here, would be here. Yeah, that's it. We have a shadow here and here. So now it's already perfect, but if it wouldn't be perfect, we just calculate the angle. Yeah, the angle we have to move, because as I said, we use the angle axis, so the angle around the normal. So for example, if the red ball would cast a shadow here, we need to rotate it to here. So this is a normal here, and this is a normal, and we rotate it around this normal. And then we have angle axis. And now what we do is calculate the rotation. So we have the shadow. The shadow is position I minus position I minus 1. We rotate the shadow, and then we set the whole thing back here, position I minus 1. It's just subtracting and adding the things again, so that we just can rotate it on the plane. And we get the signed angle by just comparing the projected bone and the projected pole on the plane normal. So here's the normal. And this is, or maybe let's take blue. This is a vector, and this is a vector, and these two vectors have an angle, 45 degrees, for example. So this makes 45 degrees on this normal, and then we rotated it on this plane. So a little bit confusing. I hope you understand it. It's not that simple, because we're dealing with planes. I did my very best to explain it to you. Okay, let's do the rotation so that it really looks right. So here's a pole, here's a target, and this is our asset from the beginning. And it looks way better if we have proper rotations. I'm getting briefly over it because it's not something you just write down. We need some of the start state, so the state on init. We need the direction from one bone to the successor, the rotation of each bone on start, the rotation of the target on start, because you can also rotate the target and it affects the last bone, and the start rotation of the wood. And here we go. Just init those arrays, as always. Set the start rotation of the target. No, here's the start rotation of the bone. And here you get the direction from the current to the next target for the last bone, or from the current to the next bone for all. Okay, during the resolve state, we do the following. We get the current rotation of the wood bone and compare it with the difference from the start. The other things are just the same, stretching forward, backward, and so on, the pole, and here we have the position and the rotation. And the rotation is really that simple. The rotation of the last bone is just scarce rotation with the target, and the rotation of the other bones is just the rotation from the start direction to the successor in comparison with our current rotation, and multiplied with the start rotation. So for example, if this is our bone and this is the successor, and this is the successor now moved here, then we have the start direction, the current direction, and it's just this rotation multiplied by the initial rotation, and then you get the rotation right. So it's really that simple. Yeah, and that's all for this video. It's a long video, but I have explained everything. So Leave a like if you like such complex videos, or just leave a comment if you want more simpler videos. Subscribe to my channel to get more straight to the point tutorials.